In this video, I will define the supremum and the infimum of a set. These are concepts similar to maximum and minimum, but more useful. In the next video, I will extend these concepts to functions. The notion of maximum of a set is often insufficient, and I want to improve it. Let me explain why with an example. The closed interval from 0 to 2, including both endpoints, is a set, and it has a maximum, the number 2. 2 is the largest element in the set. However, if I instead look at the open interval from 0 to 2, not including the endpoints, what is the number 2? It is not the maximum, it's not the largest element in the set because it is not in the set. But it behaves a bit like a maximum, kind of. I need a better concept than maximum. I need a concept that describes both what the number 2 is to the closed interval, but also what the number 2 is to the open interval. That will be the notion of supremum. First, let's recall what the maximum of a set is. I say that the number C is the maximum of a set A when C is in A and every element in A is less than or equal to C. That's the maximum. But that's not what I want. Let's take this as a starting point to define something new. It is going to take us a few steps. Let us fix a set A and a real number C. C may or may not be in A, it doesn't matter. First, we say that C is an upper bound of A when all elements of A are smaller than or equal to C. For example, let's look at both the closed and the open interval 0, 2. For both sets, 2 is an upper bound, but it is not the only one. 2.1 is also an upper bound, and so is pi and 100 and anything bigger than 2. By contrast, if I look at the set of integers z, it has no upper bounds at all. Let's go back to the two intervals. What's special about the number 2? Of all the upper bounds, 2 is the smallest. And yes, that applies to both intervals. Great! This is the key idea. This is all I need. Let's give it a name. I am going to say that the number C is the least upper bound, or supremum, of the set A. These two phrases are synonymous. Least upper bound and supremum mean the same thing. When two things happen. First, C is an upper bound of A. And second, every upper bound B of A is greater than or equal to C. This is just another way to say that C is the smallest upper bound. For example, the two intervals we were looking at both have supremum 2. On the other hand, the set of integers does not have a least upper bound because it does not have an upper bound to begin with. Now that we have the definition of supremum, we can compare it with maximum. When the supremum of a set is also an element of the set, then it is the maximum. Back to our examples. The closed interval 0, 2 has maximum 2, but the open interval does not have a maximum, and neither does the set of integers. And finally, there is one more related definition. We say that the set A is bounded above when it has at least one upper bound. In our examples, the closed interval 0, 2 is bounded above, the open interval 0, 2 is also bounded above, but the set of integers is not bounded above. That's it! We have our new definitions. We are not done. I have only defined supremum, but we have a full second set of definitions when we talk about lower bounds instead of upper bounds. I am going to invite you to write these definitions as an exercise. Can you take the original definitions and modify them to define the new concepts? Instead of upper bound, we have lower bound. Instead of the least upper bound, we have the greatest lower bound, or infimum. Instead of maximum, we have minimum. And finally, we can talk about a set being bounded below. To complete these definitions, you pretty much only have to reverse the direction of all the inequalities in the original set of definitions. And finally, there is one more definition you may encounter. When we say that a set is bounded, just bounded, we mean that it is both bounded above and bounded below. I will conclude this video with a very important theorem. This is called the least upper bound principle, but it also has a few other names. This theorem says that if a set is bounded above and is non-empty, then it has a least upper bound. In other words, if a set has one upper bound, then it must have a smallest upper bound as long as the set is non-empty. If you think about examples, this seems to make sense. It is intuitive. All the examples we can think of will satisfy it. But why is it true? That is a deep question and beyond the scope of this video. This result is probably the most important property of the real numbers. It is the main difference between the reals and the rationals. If you take an analysis course where you construct the reals rigorously, proving this property will be a fundamental step in your construction. For now, I am just going to take this as true without proving it. In fact, some people call this an axiom. Of course, there is an equivalent theorem about lower bounds rather than upper bounds. I invite you to write the statement as an exercise.